Hello everyone. So today topic of discussion is interaction of X-rays with matter, which refers to various ways in which X-rays behave when they encounter different substances. There are various type of interaction like coherent, Compton, photoelectric pair production, photodisintegration. The first one is coherent scattering, which is also known as unmodified classical or elastic type of scattering. In this, there is change in direction without change in wavelength. We have two types of coherent scattering. One is Thomson and another is Rayleigh. In Thomson, single electron is involved, whereas in Rayleigh, all electrons are involved. In this image, we can see the incident photon is having wavelength lambda 1, and after interaction, it is having wavelength lambda dash or lambda 2. So here the lambda 1 and lambda 2 are equal, like wavelength is always same. And another thing to keep in mind is we always use low energy X-rays in coherent scattering, that is below 10 keV. So in coherent scattering, the wavelength is equal to that of incident X-ray. There is no energy transfer, we can see. And the most important point is there is no ionization, and it accounts of less than 5% in the diagnostic radiograph. Another type of interaction is the Compton scatter. In this, the interaction between photons and outer shell electron is done. And as in coherent scattering, there was low energy X-rays were used, whereas in Compton scatter, we use moderate energy X-rays. So what happened is the energy of incident photon is partially absorbed and ejected as a recoil electron, and the remaining energy as a scatter radiation, which reach the image receptor and expose it. So in the image, we can see that the X-ray are coming with a wavelength lambda 1 and the scatter radiation is having the wavelength lambda 2. And there is an angle between the recoil electron and the scattering radiation, which is known as Compton angle. It could vary from 0 degree to 180 degree. If we increase the photon energy, the theta will decrease, and if we decrease the energy, the theta will increase. Compton scattering increases the patient dose, and also it decreases the image quality because the scatter radiation will cause a lot of noise in the film. This type of radiation is very hazardous in fluoroscopy. Another type of interaction is photoelectric effect. This is one of the most important interaction. So what happens is X-ray collide with the electron in atom and all the energy is transferred to the electron. The electron will be released if the energy of incident X-ray is higher than the binding energy, and the release of electron is known as the photoelectron. The electron which is released, it is called as photoelectron. So this photoelectron travels through patient body and confer the most dose to the patient body. So the vacancy is created which will be filled by the outer electron. So the electron drop down from high energy state to the lower energy and cause the loss of energy, which is known as characteristic X-ray. So, a question can be arise in our mind like why a characteristic X-ray don't hit the detector. So the answer to this question is the energy is very small, that is it is less than 1 keV. It will be attenuated within the patient tissues and won't be able to reach the detector. So in this image, we can see X-ray collide with the electron in the atom. The electron will be released if the energy of incident ray is higher than binding energy, and the release of electron is known as photoelectron. The vacancy is created, which is filled by the outer electron and released as a characteristic X-ray. Next comes is the probability of occurrence. There should be sufficient energy to overcome the binding energy of electron. Very high energies, there is a less probability. Higher atomic number should be there and increased mass density of the material. Now what we yield is characteristic radiation, a negative ion, that is photoelectron, and a positive ion, an atom deficient of one electron. Then we have pair production. It does not occur in the diagnostic radiology and energy is less than 1.02 MeV. And interaction with the nucleus of an atom, there will be a pair of positron and electron produced. The positron and electron will annihilate each other and a conversion of mass into energy will happen. That is E is equals to mc square. It is mostly used in PET-CT. This is the diagrammatic representation of pair production. The pair of positron and electron produced, they will annihilate each other and a conversion of mass into energy will happen, which is E is equals to mc square. This is same as the pair production. So when the higher energy photon collides with the nucleus, the excess energy creates an instability that results in emission of a neutron by the nucleus. In pair production, we were getting only positron and electron, but here we are getting neutron. So other types of emission are also there, which are proton, neutron combination, or even alpha particles. We can see the higher energy photon collides with the nucleus of an atom and it releases a neutron. So this is the difference between pair production and photodisintegration. Now let's recall what we have learned. Photoelectric absorption and quantum scattering are important in diagnostic radiology. The photoelectric effect is the basis of radiographic imaging, whereas quantum effect is its bane. When the energy range of diagnostic radiology is 23 to 150 kVp. When kVp is decreased, the number of photoelectronic interaction increases, but quantum interaction decreases. Lower, however, dose to the patient is increases. When KVP is decreased, patient receives a lower dose, but the image quality is compromised. Thank you so much. I hope you find this informative.